Thanks a lot, Ala, and thanks a lot, Ken, for being here. So I will do the second introduction. So today it's not my role to give any information. I guess Ken is the one who is mainly will be giving information for all of us, including me myself. So I was waiting for this opportunity to learn a lot from his experience. So Ken had his PhD from the MIT, and then he participated in many roles in the battery industry in the last period of time. In the first Tesla Gigafactory, he was part of the team of the first Tesla Gigafactory in the US. Then he worked as well in many other aspects related to lithium-ion battery manufacturing, especially cell manufacturing in Europe, namely Northvolt, which is located in Sweden. And now he's back based in the US. And we are today focusing mainly on the battery manufacturing, cell manufacturing topics, and the Gigafactory aspects. So we will be discussing mainly on our agenda 3 main points. But as mentioned, I would like to thank Ken for the time. And I would like to mention that I proposed to other people as well to join us internationally, and Ken was really the fastest. And just by proposing the idea to him, he accepted it. So thanks very much for this opportunity. It means a lot for all of us in the Arab-speaking countries and in the Middle East, especially. The 3 points which we will discuss, I will just give an overview of our agenda, and then we will go through it one by one. So the first point is that we will try to get from the experience of Ken about the cell manufacturing steps. I guess a lot of people here doesn't know much about cell manufacturing. So we'll try to give like a semi-crash course about cell manufacturing, so to say. And Ken will highlight for us the challenges which are facing lithium-ion cell manufacturing, trying to answer the second question, which is what is the main challenges we need to take care of if we need to produce cells in different regions of the world, like namely the Middle East, for example. So a lot of people looking forward to produce, asking themselves the question why we don't have until now 1 gigafactory in the Middle East area, for example, for cell manufacturing for lithium-ion cells. And we will try really to jump to the third point of giving a general career advices for the young professionals like myself and the students, whether they are PhD students, university students, of having a career inside the battery world. And Ken was responsible for really hiring a lot of people in the past. So we would like to know his opinion about what he's searching in candidates and trying really to fill the gap. So those are the 3 main points I would like to propose. So again, thanks a lot, Ken, and pleasure to have you.
Great, thank you very much. I'm honored to be here and honored that you asked. I do feel that, obviously I'm with my gray, slightly balding hair. I'm nearing the end of my career, but when I was younger, many people took their time to spend with me to help me build my career. So this is part of it. This is what people do for people, and I'm always happy to help out. So
thanks, Paul.
Yeah. With that, I think you probably wanted to dive into cell manufacturing, and maybe you could bring up an overview. But I'm going to give a couple of generalized statements to set the stage, and they are going to come across as very negative, and almost like I'm talking everyone out of doing lithium-ion batteries. And I say that because I don't want you to think that I think doing battery cells is a bad idea. It's because almost everyone I have ever met who has not been in cell manufacturing for at least a couple of years completely underestimates how hard it is. Mm-hmm. It is really hard. So I'm going to give you some examples to set the stage. Then we'll get into the technical side. Again, I don't want you to take this as extreme negativity. Oh, he doesn't think anyone else can do it. Oh, that's not what I'm saying. Take it as a challenge. Okay. take it as a challenge, but take it as a warning as well. So when we set up the first Gigafactory with Tesla, and the partner for cells was Panasonic. And I was in the cell quality group. So we analyzed, we would tear apart cells, we'd open them up, we'd look at the quality, we'd test cells, and so we had a pretty good idea how different companies' cell quality was. And I would argue, certainly then and probably still, for the cylindrical cell format, there is no higher quality cell manufacturer in the world than Panasonic. Not just because they've been doing it with all their acquisitions effectively the longest, but the Japanese are very meticulous about details. That's a culturalist statement, I realize, but it really shows in, from the Toyota production method, right? I mean, they've really refined how a lot of these production processes go. So Panasonic take my word for it, that Panasonic was and probably still is the highest quality and most competent cylindrical cell manufacturer in the world. They come to Nevada. They install manufacturing equipment in a brand new factory. Panasonic's manufacturing equipment is co-designed by Panasonic. So it's not like they're just buying garbage off the shelf. They are buying high-end equipment that their own engineers have co-designed, so they know exactly how it works. They know how all the parts go together. This is why their manufacturing so good, because they're not just doing production on somebody else's equipment. They're doing production on their equipment. I think Hirano makes the coders. They maybe don't design the coders, but the cell assembly stuff. So it's Panasonic co-designed equipment, brand new equipment from Japan. They fly, it was at least 250 experienced cell manufacturing technicians and operators from Japan with translators to help train the Americans.
Yeah.
The Americans being part of the problem, because I will tell you, Americans, we're not that great at manufacturing. So you have, and I'm not talking they flew over trainers. They flew over, in Japan, the guy who sharpens the slitting wheel that slits the electrode, he's been doing it for 12 years, and is proud to come in every day to do it. I mean, this is the essence of great manufacturing. So they fly like 250 of them over for 6 months to train the Americans. The factory starts up, and this is public record. They then proceed to lose money every single financial quarter for 2.5 years.
Wow.
Okay. How is that possible? And the short answer is, making cells is really hard. You don't just buy great equipment, hand workers work instructions, which Panasonic did more than that, pour materials in one end and have cells magically pop out the other end. It is so complex. And really, when they finally got to profitability, which they've been profitable, I think, every quarter since then, I can't tell you what the yields are because I'm not allowed to, but basically it was just a battle of getting their yields up, meaning how much product was in spec versus how much product just barely missed or missed specification at any particular step. And every single step of the cell manufacturing, of which there are probably thousands, every one, there's a team battling, with an axe or a hammer, trying to hammer down, get the yield up and figurative hammer, not hammering, but really working to get yield up. And it wasn't like they just solved a problem and were profitable. It was hundreds of problems. Not because the equipment's bad, not because Panasonic doesn't know how to make cells, but really, you had new people on equipment They got training, but there's this knowledge that really helps. And I think part of the mistake that people make in this day and age is they think everything's very automated, which it is. There's sensors, there's cameras, there's inline x-rays, there's, all this super fancy equipment. And they think that that means that people aren't important. And that turns out to be very wrong. Yes, in an ideal world, we would have robots make everything. But it just doesn't work that way. So another example, then let's take, and this is hearsay, meaning, let me translate that. This is what I have been told by somebody who was told something. So this may or may not be accurate. But from what I heard, LG Chem, when they set their plant up in Poland, LG Chem, by the way, also a really experienced, great battery manufacturer, and they set their plant up in Poland. They basically had the same problems. Not necessarily the exact same technical problem, but they had yield problems for the first 2 years because new employees on a new line. And then you look at startups, of which I've worked at several, and guess what? They also have problems. And it's not because they're startups and they don't know what they're doing. And that's what people seem to think, is they say, oh, these startups, they don't know what they're doing. But it's interesting to see the established manufacturers also struggle on new factories. It's really across the board. I think as we build more and more of these, we will learn how to learn and we will get better at it. But with that sort of dire warning, let's dive into cell manufacturing.
Yeah, but before we dive into cell manufacturing, this is very interesting, 2 examples, because the first thing, let's take the first. I have few comments on this two stories about Panasonic and LG. So I guess you meant when they fly to Nevada to build up the first Tesla factory, right? This was in cooperation with Panasonic. So they had to fly, you said 250 Japanese people plus minus. Is it because the lack of experience, or is it because that they do not trust that no one else will be able to run the manufacturing the way it should be?
No, it was simply it was the lack of experience. I mean, you set up this factory and you hire people. The phrase is off the street. You're not really hiring them off the street. You have a job fair and you hire engineers and you hire operators, and one person may have worked in a paper mill, or one person may have worked on an assembly line making air conditioners, and somebody else, and people with reasonable experience but not making batteries. And you say, so what? So if your job is to take this thing and put it in here, and I write you a work instruction and say, you pick this up with the left hand, the handle has to face this way, you pick this up, you inspect it, you put it in there, that's that step, do it. And you say, great, but it doesn't work right. And why doesn't it work right? Well, because they don't know what the cup's made of, and they shouldn't have to know what the cup's made of, and they shouldn't have to know what this is, and they shouldn't even have to know why they're doing it. They're just doing, they're just doing their task. But the interesting thing is, and this is some weird human psychology thing, it does matter. It really does matter that your people have to understand why they're doing what they're doing. On paper, it doesn't matter, but in reality, you get better quality, better yields, better output when the people who work on your production line, or the engineers or the designers, understand the motivation of why. Now, look, anybody on this call clearly cares, right? So you've got the intent, but you also need to understand, let's say you were an engineer and you were the engineer in charge of mixing. Okay, so you're a production engineer, and we'll dive into production in a moment. You're in charge of mixing. Well, mixing what? Well, you make a slurry. You take your electrode materials that are going to be on the anode or the cathode. You mix them up in a slurry, a wet slurry process. And that happens in a certain order, at a certain temperature, over a certain time period. Some mixes take 4.5 hours to get done, some 6 hours. And you say, well, it doesn't matter because you're a production engineer. The recipe I have says that first I add this amount of this, and then I add this amount of this, and I dry mix it for this long, and then I add some liquid and I mix it for this long, and then I add some of this powder, and then I add some pixie dust, and I mix it for this long, and then I measure my properties with a complex rheometer, and I get these properties to prove that my quality is good, and then I can send it to the next step. I am telling you that's not good enough. Because if that process engineer doesn't understand why these get mixed dry first, why then the liquid is added, why this other thing is added, and you have to wait before adding the other thing. If you don't understand why, it makes troubleshooting really hard. It just doesn't work as well. Your yields aren't as good. And when that engineer and the operators, especially, don't undervalue your operators, when they understand why, then they are cued in saying, well, that doesn't look right. That doesn't look right. And they catch stuff. But if you treat them like little chess pieces that just are supposed to move from one, oh, this is a pawn, they only move this way. Oh, this is a rook, it only moves this way. And you treat them like
it
that,
will never work.
You're going to get exactly what you deserve. You're going to treat your workers like little chess pieces, and that's exactly what they're going to do. They're going to act like little robotic chess pieces, and they're not going to. How's that saying? French guy, Yvon Chouinard, he had this saying, take care of your people and they will take care of your business. Now, look, we're way off the technological part of what. Now I'm getting philosophical. Let's get away from that. Let's get into the technical. We can have a whole philosophy discussion when we talk about career development.
That's right. That's right.
Okay, but I'm going to make you pull up something. Do you have the mixing? I know I saw you had a mixing slide.
Yeah, that's right. I have the whole processes here from this nice guide, and mixing. We have to search for it. Operating vacuum, dry packaging.
All right, you know what? I can talk it through anyway. But the mixing, the coating, and the drying comes before calendaring. Okay, so. Actually, let me ask you a question. Is everyone on this call probably read in enough on battery manufacturing that they
know
what an anode and a cathode is? Because I can explain it pretty quickly.
You can do this. Feel free to do it.
Okay. So you all know that a battery, you can charge it and you can discharge it. And I'm speaking in generalities. So there's always exceptions to what I'm going to say. But in general, take what I'm saying as faith. There are exceptions. So some things I say won't be exactly accurate. So a battery cell, think about your little, I wish I had one. Maybe, let me, hold on.
Okay.
No, I can't. I was looking for like a little AA battery cell, right? And there's a little dot on the top that's the positive, and then the whole can that's covered is negative.
Yeah.
Negative what? You know what? You don't need to be an electrical engineer. There's two sides. There's a positive side. There's what we call by convention the positive side, which is going to be the cathode, and the negative side, which we're going to call the anode. And new people mix this up. Well, here's your way to remember that. Some people like cats. If you like cats, you're positive about them. Therefore, the cathode is the positive electrode.
That's a very nice way to remember it. Because even me, I used to make them for a long time, but then I had to remember it, in a certain way, that cathode is the positive and anode is the negative,
Yes.
But this is a nice way.
I'm not saying you have to like cats, but some people like cats. I like cats. And if you like cats, then you're positive about them. That's the positive electrode. The anode is the other one, so it must be the negative. Okay. The cathode, let's start with the anode. The anode, the negative one, in a lithium-ion battery, again, there's exceptions to this. There's so many exceptions, is generally made with three types of components. The main anode component is graphite,
Mhm.
okay? And that can be synthetic or natural, that's mined out of the earth. A conductive additive, like this is where people get into carbon nanotubes, or they'll be looking at carbon black, or conductive additives to help electrical conductivity, and a binder. By binder, which is the term in the battery industry, glue. You got to glue it together, right?
Mhm.
And then the anode is then, so these things are mixed into a slurry so that they can be coated onto an electrode sheet or foil. In other words, you've got this chemistry going on in your anode material, your graphite, your conductive agent, and the binder that holds it all together. But how do you get the the electrons in and out? So you could see on the left side of this, you've got the graphite layer, and then you see those little E's with a minus on the left-hand side going out. Well, those go out via basically a foil. And in the case of the anode, electrochemically, it happens to be copper. On the cathode side, and what it says there is LiMo, which means a lithium metal oxide. M could be cobalt, it could be manganese, it could be iron phosphate. Well, actually, that's different. That's not a metal oxide, it's phosphate. But again, there's exceptions. It could be nickel, manganese, cobalt. It could be nickel, cobalt, aluminum. It could be, anyway, it's a metal oxide. So in a corollary to the anode, in the cathode, you have this lithium metal oxide, sometimes a conducting agent, and a binder, a glue. Now, there's many other things you can put in there. Now, the cathode foil is aluminum. The anode foil is copper. You know how you're going to remember that? Copper starts with C, it goes with anode, which is A.
Mhm.
Cathode starts with C, it goes on aluminum, which is A. In this case, C goes with A goes with C.
Yeah, that's
Now that
exactly
you've heard
how
that,
I do remember it as well. That's exactly
you're
how it.
never going to
Yeah.
forget it now that I've
Yeah.
said that. But if you try and just blindly memorize, the cathode, is that copper or aluminum? And I can't remember. It's reversed for the letters. Now you will never forget it. So going back to mixing, the first step. Well, actually, no, you can leave that. Sorry about that. Go back to that one. Let's just finish up with what a battery cell, how a battery cell works. So you've got your anode is your negative electrode by convention. Your cathode is your positive electrode. People like cats, it's positive. I'll keep repeating that. And then you need lithium ions, in other words, lithiums that have a positive charge that are missing an electron, moving back and forth. They literally physically move back and forth between these two electrodes. But one of those electrodes, the cathode, is positive, and the other one, the anode, is negative. And if you put them together, just like if you put a piece of metal shorting out your battery, they'll short and you'll get sparks and a fire, and it won't work. So you have something in between it called a separator, which you can see in the middle. And a separator is a microporous, it's usually a microporous, meaning little tiny holes, little tortuous holes in plastic.
Mhm.
Why plastic? It's usually polyethylene or polypropylene. It's plastic because that electrically isolates the cathode from the anode. So you have cathode, a separator, and an anode. You can squeeze those together and the cathode doesn't short circuit to the anode. But the lithium ions can't just hop through air. So you usually put in an electrolyte. In the majority of cases, the electrolyte is a liquid. It's an ionic liquid. If you you could go look up electrolyte on the internet, pull up a safety data sheet, which you can find from somebody. You'll see about 5 different ingredients. There's usually like 12 because there's a bunch of trade secrets. It's a mixture of organic solvents. Why do I say that? I'm not expecting you to know what an organic solvent is. Organic solvents are flammable. An organic material is well, you know what else is organic? Gasoline is organic. Okay. And gasoline burns. And organic solvents in general, are flammable. Polyethylene is a plastic. Think of it as frozen gasoline. It'll also burn. It's just not quite as explosive like gasoline. So the electrolyte is primarily usually flammable, depending on the electrolyte you use. And they put some other things called salts in them to help the lithium ions transport back and forth. Think of it as like a boat helping ferry people between the anode and the cathode. The salts are the boat, and the water is the organic electrolyte. Okay, so we got to make this thing. Let's get back at it. You got to make that graphite layer, which is coated on aluminum. I'm sorry, I got it wrong, which is an anode. So it's coated on copper because it's the anode. So it's coated on copper. And then you've got this cathode material, which is coated on aluminum. So let's go to mixing. So the first thing that you do, and remember, let's take a basic anode. I said that the anode is graphite, a conductive agent. You're talking very little bit of conductive, 0.5% by weight, 1% by weight, maybe 2%. See, primarily graphite, a conductive agent, and a binder, aka the glue. Standard glue, the standard glue in an anode, and again, always exceptions to this, are carboxymethylcellulose and styrene butadiene, a low molecular rubber. Why two different glues? Well, it turns out that one of them, the CMC, is good at cohesion, which is gluing the graphite to the graphite, and the SBR, the styrene butadiene, is good at adhesion, gluing that whole thing to the foil. It's the anode to the copper foil. But there are other binders and other binder combinations you can use. Now remember, you want to use as little binder as possible, because binder, the only thing it does is glue things together and then take up space that doesn't help you with a battery being a battery. So you try and minimize that. You make it too small and you don't get good adhesion, and your electrodes fall apart either immediately or 300 cycles down the road. So there's a big sort of tug of war between minimizing the binder content. The other thing, but this is where batteries start to get hard. So you say, okay, well, Ken told me I got three things. I got graphite, I got a conductive agent, and I got binder. Oh, but the binder's really two different binders. Okay, so I got four things, and then I need to mix them all together. Do I dry mix them, or well, no, I need to put them on something that I can coat. So you use water. So you put in water, and you think like, well, if like I'm baking a cake or I'm making bread or something, just put all the ingredients together and just mix them up. Yeah, except that doesn't work. You get really bad batteries when you do that. So there becomes a whole, it's not just science. There's a lot of trade secret and intellectual property that different companies guard very carefully about what order you mix what. And how long it has to mix. Because remember, for instance, the CMC is really good at binding the graphite to the graphite, but the SBR is good at binding all of that to the copper electrode. And if you mix them in the wrong order, it doesn't work as well. Your tests will come out the same. Your viscosity tests, they'll be the same. It looks the same. It's a big, dark, black, gooey liquid mix, but when you get to the end cell, the performance is totally different because you mixed it in a different order. And you're going to say why, and I'm going to say, look, we could go into it, but we'll never get through everything. My point is, and yes, there are scientists that figure out this order works for these ingredients, and the workers on the battery line, you should just hand them their instructions and say, put this in for this long, and put this in for this long, and put this in for this long. And I'm telling you that those people who do that, if they understand why you put one in first and why you put the other one in next and why you mix for a certain amount of time, your production goes better. It's that human element. So the next thing that you do, now that's the anode. The cathode, I don't want to get too detailed. Electrochemically, in a lithium-ion battery, carboxymethylcellulose and styrene butadiene rubber, those things that were soluble in water, are not electrochemically stable on the cathode side. In other words, electrically and chemically, they chemically break down because of the electric potential. So you really usually use a fluorinated binder. It's got fluorine on it, which makes it really expensive. But those aren't soluble in water. So now you can't use water as your solvent. The other thing is that if you're making a high-end NMC battery, lithiated nickel manganese cobalt is very reactive with water. So you do this in a dry room. So you can't use water for that reason either. So they usually use NMP, which stands for N-methylpyrrolidone. It's a little unfortunate that NMP sounds like NMC, which is nickel manganese cobalt, but yeah. NMP is a solvent. It is like diesel fuel, not technically flammable at room temperature. It's a great processing solvent. It's not reactive, it's not very reactive with anything. It has a very low vapor pressure. It's great at suspending various types of particles. It's really wonderful, except it's super hazardous to humans. Kind of like lead is great for plumbing connections, except that it's toxic. Like asbestos is an amazing insulator, but is really bad for your lungs and causes cancer. NMP is an amazing processing solvent, but it's really dangerous. So you've got this really dangerous chemical in your anode. You've got water in your cathode. You've got water in your anode. You've made your slurries. They've got their glue. They're this mixed up goo. Now you're going to coat onto your foil. Anode coats. Anode starts with A, coats onto copper. Cathode starts with C, coats onto aluminum. And what happens is there's many different coating techniques, but think of, you almost, extrude is the wrong word, but you have these slot dies usually, and you pump this fluid out and dispense it while the foil is going through this long system. And that long system takes the bare foil, wraps it up through, gets coated with a thin layer, and then that gets run through drying ovens, because you need to now get rid of the solvent now that you've coated it. So when you're drying the water, you just evaporate it. And when you're drying the NMP, because it's toxic and expensive, you need to recover it. So there's different recovery systems. This is millions of dollars in expensive equipment. You need to recover it and then re-refine it. So now you're running a chemical refinery to refine NMP, which is, again, causes birth defects. It's super hazardous to humans. So everyone's wearing face masks and respirator cartridges. The interesting thing, and I'm not going to throw out all the problems that happen at every stage, but drying is a great example of how complex this is. And this is where science becomes super important. So you think, okay, so I've got this wet slurry, I've coated it on this thing, it's got a bunch of binder glue in it. I just need to evaporate off the water in my anode, and then it'll all be stuck together. And the answer is, yeah, that's true. If you dry it too fast, though, what happens is the water is coming up to, you have this, think of having this layer of wet electrode goo on your foil. And as you're evaporating it, it's only evaporating from the top surface, right? It's not evaporating through the foil. So you have this transport problem where water molecules are moving up through. And what they do, because the binder is dissolved in them, they effectively drag the binder up with it. And if you dry your electrode too fast, all of your binder, your CMC and your SBR in this case, when you're finally dry, most of it's up at the surface and not a lot of it's down at the bottom. And if your SBR is moving up through up to your surface, well, the SBR is what holds your electrode to your foil. So now you're going to have delamination problems.
Mhm.
And if you move too much of your CMC up to the surface, then your regular electrode doesn't hold together very well. Added to that, now your top layer surface of your electrode has a ton of glue in it. And now your electrolyte doesn't wet well. Your lithium ions don't move in very well. And so the drying regime is super important. This is why your drying ovens are sometimes 70 meters long. 70 meters is a long drying oven.
Yeah, that's right.
And then you say, okay, well, we'll make a really long drying oven, and that's really expensive. Oh, by the way, it's got to be in a dry room because you can't have any water vapor around. Well, for the anode, obviously you can, but for the cathode, you can't.
Okay. So let me
And
stop here because you mean the drying is in a dry room?
well, the ovens usually are sealed and don't go through a dry room. And then, so for the cathode, the rolls that get coated are in a dry room. Dry
Ah,
rooms are also very expensive.
that's right.
Then it
Yeah.
goes into this oven, which is usually not in a dry room.
Mhm.
And then it goes back into a dry room to get rolled up.
Mm.
So,
But does
your
old
dry,
manufacturing, because before jumping coating, does old I'm not talking about LG Chem and Panasonic. I'm sure that they are doing it in a dry room. But does all the batteries which we have in the market really tries, is there is any standard to say doing this in a dry room? To my knowledge, there is not. And
well,
there are problems which happening because of not doing the process in dry rooms, to my knowledge.
that is true, but there are, like I said, there are always exceptions. For instance, LFP, which is iron phosphate. It's a different type of cathode. There are many manufacturers that actually do their cathode using water. They do an aqueous process because two reasons. You say, wait a minute, Ken, you just said you can't do aqueous for the cathode for two reasons. Because because you need a fluorinated binder to be electrochemically stable. And secondly, your lithiated cathode is too sensitive to water.
Mhm.
And then I say, yeah, but LFP's voltage is lower. So guess what? You don't need a fluorinated binder in the cathode because the voltage doesn't go up as high, and LFP is not as sensitive to water. So in the case of LFP manufacturing, you can use water as your solvent for your cathode. There's always exceptions.
Mhm.
And if you're really quick, you could also get away with not doing it in a dry room.
Okay.
Right? I mean, how much water exposure is too much? Well, this is not digital. It's not like, oh, too much, oh, too little.
Mhm.
No, if you expose it to some moisture in the air, what happens? Well, you get some lithium hydroxide, you get some metal oxides. So what? Well, your capacity goes down. That water in there will also react with form the salts in the electrolyte that'll form hydrofluoric acid, which degrades your anode and your cathode, and your capacity is less and your cycle life is less. And
Yeah.
it's not like the cell dies. It's not like the cell explodes because it was exposed to water. It's just not as good of a cell.
Yeah. That's the main point which I wanted to make is that you said dry rooms are expensive, and anyone who works in a dry room, including me, knows that they are expensive. But let's give, because there are some audience as well who doesn't know what is a dry room. So let's give a quick definition for it, please. So what are the conditions in a dry room is?
So in a dry room, well, you can define it how you want. In general, the industry standard for a dry room for manufacturing lithium ion cells is something that has a dew point, and I'll get to defining that, at the dry room temperature of minus 40 C.
Mhm.
Meaning at 40 degrees below, if you had a surface in that dry room that was at minus 42 degrees centigrade, water would condense on that out of the air. Now, if you've ever lived, many of you probably have not, in a really humid environment and it gets cold outside, you'll get water droplets forming on your window.
Mhm.
Because there's a lot of moisture in the air and it gets cold, and it's no longer the air. When the air gets colder, the water drops out of the vapor phase. What a dry room's definition is that it drops out of the vapor phase at -40 centigrade. Doesn't mean there's no water in the air. It means there's not a lot of water in the air.
Yeah.
It's not zero, but it might as well be.
Yeah, I remember the first time I went inside a dry room and I seen the -40 degrees, and we were not wearing heavy jackets by this time. You don't feel that cold inside because of humidity, I believe. So you can work inside in this very low temperature, and it was like a new experience. But I wanted to raise this point to make the aspect related to cost, because we see that we're just in the first steps of manufacturing, and we are talking about huge amount of cost of investment. And I want to translate to people the difference, where the differences come, and it will build up, by the way, between a good cell and a bad cell.
Yeah.
So this is one of the things I wanted to stress out.
Yeah. Good cell, less good cell, slightly even less good cell. Again, there's this continuum. And that's the problem. Some people like me, because I was in quality, I say, you cannot let your dry room get above -40 C. Well, you can. Your cell performance is probably not going to be quite as good. It's still going to be in spec, maybe. I don't know. Got to try it. You can cut corners here and there. And this is, if you were going to cut corners on something, I suppose this is probably where you do it, because it's not safety related. But again, if you're already looking to cut corners when you're building a cell manufacturing plant, you probably should not be making lithium-ion batteries.
Yeah,
because you're not coming in with the right attitude. Again, that's the human element, not the scientific reality.
Yeah.
So and look, the drying's complicated because I said it's called binder migration if you dry too fast. But you can actually dry fast at the beginning when it's really wet, and you can dry fast at the very end when it's all stuck. There's 4 phases of drying, and you can dry at different. So you got zones in your oven, and you can adjust the different zones, and depending on your foil speed and the length of your oven and what your binders are and what the size of your particles are, you can change your dryings. It's super complex. Every stage of this is super complex. All right, so let's get out of drying.
Yeah,
because we could spend 2 hours on drying. Literally, I could talk for 2 hours on drying. You don't want to hear about 2 hours of drying. And I'm not trying to scare you by telling you how complex it is. I'm trying to demonstrate that this is a very complex process. But what that means is there's lots of space for you to become an expert in an area and be super valuable. When we get to the career side of this, right? It's not like you're injection molding a plastic thing and there's 20 million experts out there and you have nothing to bring to the table. No, we have an industry with a super complex set of problems, and you could become an expert in any one of them.
That's right.
Or helpful in any one of them and be helpful. No one person, certainly not me, understands all of these processes well.
Exactly. And this is a very important message, because people think that we will discuss it in the career part, but just a quick comment on it. The mentality, especially that we have in the Middle East, is that some people in general tries to understand many things and say, okay, we will be good if we understand many aspects of the thing, how it works. There is the culture of specialization or having just one aspect to the depth it needed. So someone who's called a drying expert, you will not find rarely those people in the Middle East area, but it's easy to find them, for example, in Germany, in Japan, in the US, in specialized nations. You will see people who are really spending 10, 20 years doing the same thing again and again, and just every day they get just a little bit of step. And if you ask them about coating, they will tell you, I don't know the answer, even that if they know it, but they will never jump out of their specializations. So this is as well something which is, it's like not a common sense culture, I would say, in the Middle East, because I come originally from Egypt. But I did see this because I live in Germany. Of course, how the German people as well, they are like the Japanese people, they are very specialized. So this is the main culture here. And this is really a very strong message, which we need to deliver to everyone who's hearing us today before jumping to the next one.
Sure. So let me get to calendaring. Let's get through this, because otherwise we can go on forever. So
That's right. Yeah.
calendaring. Some people call it pressing.
Yeah,
it's the term people use. I use calendaring. Other people I've talked to call it pressing. It doesn't matter. It's basically two giant steel rollers that here we go, that you run through here. Here we have a top roller and a bottom roller. They can be heated, they can be cooled, they can be heated and cooled, they can run at different rates. They generally, you don't do that. And what you're doing is you've coated on this electrode, you've dried it, but now there's a lot of pores left over because you basically evaporated out the water. So it's a little too much like a sponge. And that's fine if you don't care about high energy density. But if you do want to pack a lot of energy into your cell, you need to control the thickness of those. And calendaring is basically you are crushing. I mean, these are big rollers. Mm-hmm. You are pressing the ever-living snot out of this electrode to a certain level of density. Now you could say, oh, well, let's put more energy in my electrode. Let's crush it even more. Well, then your pores become too small and you can't get your lithium ions in and out. So there's a balance there. If you crush it less, you get lithium ions go in and out faster. It's faster charge and discharge, but you fit less energy, total energy in your cell. If you crush it more, now you can pack more electrode in your cell, but your charge and discharge rate, how fast you can charge, how much energy power you can get out, goes down. So there's a trade-off, and that's all part of the cell design. When you design your cell, that's all considered. And lithium ion cells that go into like a power tool, like a drill, generally don't have as much energy as the one that goes in your car, but they have more power per cell because they're designed for power tools. It's not the same cell. So yeah, that's calendaring. We can just, at the end of that, and of course, all of these steps have multiple quality control steps. Mm-hmm. Beta gauges, looking at thickness, and people cutting out little pieces and doing moisture tests on them to make sure they haven't been exposed to too much moisture, and adhesion tests to make sure that your adhesion is good to your foil. And yeah, there's tons. Yeah, I'm skipping by all of the different quality control steps, which are also all areas of expertise that one of you could become an expert in. So the slitting, generally, yeah, I mean, this is reasonably accurate. When you're coating, for instance, take that lower lane where it says prismatic and cylindrical, and you see that the coating is actually in little lanes. You can do that, or if you're doing prismatic, you might just have one lane, but then the left side would be an electrode and the right side would you'd slit it down the center. Now remember, when you're coating these things, if those edges, you'll have high edge problems, you'll have low edge problems, you'll have width problems. All of this stuff needs to be in specification. Well, how close does it have to be? Oh, 0.5 millimeter. You're sort of, you better not be off by more than 0.5 millimeter, or you're in a lot of trouble, and it can actually become a safety issue. Mm-hmm. So, when you're slitting it, little knife blade sticking down, literally slitting this. If your slitter cutting wheel isn't sharp enough, you could get a little metal burr that sticks down, and if that burr sticks down 70 microns, remember, 100 microns is 0.1 millimeter.
Yeah.
So if you have a little metal burr that's 1/10 of a millimeter long, that is a serious safety problem. You'll probably catch that in formation and aging when your cell catches fire. But really, you don't want those happening. So we are talking about very exacting tolerances. and you say, okay, so this goes really slowly, and you're really, no, it doesn't go really slowly. These things are moving at 20 meters a minute.
Mm-hmm.
And sometimes when you're slitting cylindrical cells, you could have 7 lanes. So 7, 10, 12 of these slitting wheels are slitting, and they're all getting rolled up separately. And every single slitter has to not make a burr bigger than, 10 microns, 20 microns. Remember, 100 microns is 0.1 millimeter. So you're talking really more like 100th of a millimeter is really where you'd like to be on your burr size. 100th of a millimeter.
Yeah.
Okay. I could go on about how hard every step.
I would just like to give a very quick overview about pouch, prismatic, and cylindrical cells. Who doesn't know what is pouch prismatic, I have a picture here, and we will jump back to continue. So I have a cell format here. I guess I can use this one here from the cell formats. We can use this one. So this is basically a pouch cell. So it's like this type of cell which we have, for example, in our cell phone. This is a prismatic cell, which is hard case cell, and this is a cylindrical cell. So this is exactly what was mentioned in the other side. Those are the 3 common types which we have for lithium-ion batteries, more or less. So I just wanted to show this because it was mentioning here the 3 aspects, and I will jump back to.
Yep. So once you've gotten your electrode made, which is the hard part, in my opinion, here's an interesting little thing. People look at all these steps, and we'll go through the cell assembly steps. And when you walk through a lithium-ion manufacturing plant, if you ever get the opportunity, it's fascinating. And it's interesting because everyone seems to think that the cell assembly, this is from the slitting on, is the hard part. And yes, cell assembly is really hard. But I think, and they all sort of dismiss electrode production. And that's because you mix a bunch of stuff together. It looks like black goo. You coat it onto a foil. It looks black. You press it down. It looks black. You slit it. You're like, how hard can it be? But there's all these chemical nuances in there. But people can't mentally grasp what's going on a molecular level, so they don't think it's hard. The cell assembly, when you see cell assembly equipment, you can go watch YouTube videos watching like stackers, like go look up, Z stacking video on YouTube. You'd be like, whoa, that's really complex. And the thing is that we all as human beings can look at that. We can visually see how complex that is. So we say cell assembly is really hard. It is hard, but it's not as hard as mixing and coating. Because you don't get that visual feedback of what's going on in mixing and coating. In my personal opinion, the hardest part of cell assembly is the electrode production. It's the mixing and coating, because you can do it. It's not hard to do it. It's hard to do it right. But it's very hard to tell if you've done it right. The second hardest part is formation and aging. Yeah, which people also dismiss, because you can't see what's going on, and it's molecular. The easiest part is cell assembly, which is still really hard, but everyone thinks it's the hardest part because you look at all these machines doing their little fancy machine stuff, and you're like, whoa, that's really complex. Yeah, it is. Trust me, it's not the most complex part. All right, vacuum drying. So you will then generally vacuum dry to make sure any water, you want to make sure, again, you don't want water in your cell. You want no water vapor, so you will vacuum dry. That actually serves 2 purposes. Gets rid of any residual solvent that might be left, especially in the anode, because in the anode, the solvent was water. Okay. And sometimes people dry cathodes. Sometimes they don't vacuum dry cathodes. Sometimes they vacuum dry it to get rid of a little extra NMP. It depends on your manufacturing system. Okay. Some people do not vacuum dry cathode. Some people do. And is there a right or a wrong? The answer is depends what your other systems before that were. Depends if you're using a dry room. Depends who your material supplier is and how good their supply is. Depends how your oven works. Depends. But anode, you definitely dry. So after that, we now we move into cell assembly.
Yeah,
and cell
which
assembly. Go ahead. Yeah.
will be more meaningful for the people, I guess, because
Yes.
this is what they see in videos and so on. I guess I believe so.
Yep.
Yeah.
Cell assembly. So in a cylindrical cell, you take your anode and your cathode and your separator, and you wind them all so that you have separator between your anode and your cathode.
I guess I have yeah.
Yeah, wait, it's okay. I imagine it, you're rolling it up like you're rolling a cigarette or a cigar. And it's a spiral with anode and cathode and separator all wound up. But there's also, you got to add tabs, because how are you going to connect this stuff? So on your anode and on your cathode, there will again, there's the exception. There's Tesla's tablets. I know. But generally on your electrode foil, the copper for the anode or the aluminum for the cathode, you will literally weld on with usually a resistance weld, a tab. So a little piece of metal that sticks out. And then on the anode, that will get bent in on these jelly rolls. They're small. So it gets wound up super tight, all wrapped up in separator. And then this gets inserted into a can. So it gets, wish I had some demo pieces. So if this is my can and my jelly, this was all rolled up, it would get inserted. Okay. But I got to connect it. So you'll have a stake down the center, which welds your anode to your can. And then on the top, well, you'll leave it open because you got to fill. Eventually what you'll do is you weld your cathode tab to your top cap that'll later get crimped. You'll weld that little tab to your top cap that'll then finally get inserted and crimped into your cell. I need better props. But every one of these steps, the welding has yield problems, the insertion has yield problems, the winding has yield problems, the alignment of the anode and the cathode, the x-ray of the system to make sure that your alignment was right, because now once you've inserted it, you're blind. Then you do, I suppose you could do flanging. You'll make a little, for cylindrical, that cap needs to sit on something. So you do grooving or beading or flanging, whatever you want to call it, where they put a little shelf in the can. So you come in with a little, it's almost like a blade as this thing spins, and you put a little groove in, which is what the cap will sit on. But before you put your cap in, you need to get electrolyte in. Electrolyte, remember, is this liquid medium by which lithium ions can transport back and forth. They don't just hop through air. Not that there's a lot of air in there, but they do need some transport medium to swim across, basically. So you put in electrolyte. Small cylinders are pretty easy. The electrolyte soaks into the anode, the cathode, the separator, because they're all porous. Happens fairly quickly. And then eventually, well, okay, let's leave it at that for now. For both prismatic and pouch, there are generally two ways in which what we call jelly rolls are made. So this, before it goes into a can or the final pouch, it's called a jelly roll. Probably because cylindricals looked like little rolled up jelly rolls. One way that it's done, here's the where it says prismatic. You see it says winding flat. So basically, you do the exact same thing. You spin up this wound assembly, and then you flatten it. You smash it down, so that if you can zoom in on like that hot pressing part. Now it's hard to see, but you can see that when you smash it down, it's almost ovally. It's because you've collapsed this thing. It's got rounded edges. And that's probably the fastest and the easiest way to do it. The other way that people do it is what you would call stacking. And he's got stacking shown by the pouch, but you can do it for prismatic too. And there's two different kinds of stacking. You can do Z stacking, where basically your separator goes back and forth, and you place an anode, place a cathode, place an anode, place a cathode, like building up layers of a sandwich with separator weaving in between. The other way is some people will take discrete, they'll put an anode, a sheet of separator, a sheet of cathode, a sheet of separator, and they'll stack the whole thing up like a sandwich. Now, how hard can this be? Oh, go watch some videos. Go watch some videos of Z stacking on the internet, and you go, wow, those things are going in really fast. But here's I'll go off on a tangent for a moment. You want to maximize the amount of energy in your cell because you're going through the expense of building it. So you want to fill as much of that volume as you can. There's a failure mode that I don't think we'll get into, but basically your anode needs to be bigger than your cathode, both in terms of how many lithium ions it can accept and geographically. In other words, it needs to overlap. So if you take a cylindrical cell, lithium ion cell, and you discharge it and you get in a fume hood and you unwrap it, you'll see that the width of the long anode is wider than the width of the cathode. And if you take a prismatic cell, or the sheets, if you were doing singular sheet stacking, the sheets of the anode are wider and longer than the sheets of the cathode. And that is a safety related issue. And you say, okay, great. So when we stack them, we just need to make sure that everything's centered. You go watch some of those videos and watch how fast those sheets get stacked. And now I'm going to tell you that on a not great quality cell, the anode might be 2 millimeters wider than the cathode. So you have maybe plus or minus 0.5 millimeter of alignment on all four sides, corner to corner. And you watch these stacking videos, and it's stacking these things at sheets per second with sub-millimeter alignment accuracy. Now, it's not done by a person, it's done by automated machinery. But if it gets it wrong, how do you know? Because that's a safety issue.
You will know when the cell, I guess you will know when the cell explodes, yeah.
Oh, wait, have I lost you on audio?
No, I was, okay. I was saying that you might know when it's too late, when the cell really explodes. But we can still hear you, Ken.
Uh-oh, I think we lost audio. Can you guys hear me? Say something.
Yes, we can hear you.
Okay, sorry, I lost audio. Where did you lose me?
No, I was just saying that you will know when it's too late, when the cell maybe goes into thermal runaway or explodes.
Yeah, but the problem with misaligning stacked sheets, I see there's actually a question that we should all get to. The problem with misaligning stacked sheets is it might not show up for a couple of years. And then your cell catches fire.
Exactly.
Years. So then you have inline X-rays and inline CTs and all sorts of, anyway, I'm just pointing out, it's not easy. And if things don't get stacked right, you throw away the entire cell. What was the question?
There was, I guess someone needs to ask a question. Ali, you can unmute yourself, and if your question is related to this part, please do it.
Okay, let's go on. If you've got a question, you maybe throw it into the chat, Mohammed. You can grab it out of the chat and ask it. How's that?
I would do this, yeah.
Yeah. Okay. So So after you've made this jelly roll, which hopefully while you're handling it, sometimes you hot press it to try and get it to all stick together a little bit, but you can't use too high temperature. You can't use too low temperature. Depends what separator you're using. It's very complex. Then you insert it either into a pouch for a pouch cell or into a can, meaning usually an aluminum can. You might need to weld it to a lid first. Again, it depends on your design. And then you need to seal it. In a prismatic cell, you're usually laser welding your lid to around the rim of the can. And if your pouch, you're doing a heat seal. You're not completely sealing it because now we've caught up with the cylindrical. Now you need to get that electrolyte in. So you got to fill your electrolyte. Now on a small cylindrical cell, that electrolyte you put in however many grams you're going to put in, 4 grams, 7 grams, depends on the size of your cell.
Mm-hmm.
In a giant prismatic cell, like some of these big cells, you've got a tiny little fill hole. And so you put in all the electrolyte you can, and you can't get in enough because it hasn't soaked in, because there's a transport problem. This is not like soaking water into a sponge, which, by the way, also takes time. But imagine that you have a giant sponge in a package and you put some water in one part. It's going to take time to soak through. And until it soaks through, you have 2 problems. One, you can't get your electrolyte in. You can't get enough electrolyte in because you need to get in a certain amount. And the other problem, so sometimes electrolyte filling can take 30 minutes.
Okay.
And you pull a vacuum and then you put pressure, and you pull a vacuum and you put pressure, and you pull a vacuum and you put pressure. But remember, electrolyte is flammable, it's toxic, it's hazardous, and it can't be exposed to water. Yeah. So all of this is done in a dry room.
I have a feeling.
Yeah. So let's pretend you've gotten all the electrolyte that you want in your cylindrical cell or your prismatic cell or your pouch cell. You say, okay, great, now I can seal it up. Nope, no, you can't. Then usually what you do before you do the final seal is you do a pre-charge where you charge up your cell a little bit. Usually, depending how long sometimes you charge up to a certain lower than full voltage, sometimes you go up to full voltage. And what happens is now you're starting the first form of the cell. You got to make sure all the electrolytes soaked in. So sometimes soaking can take 30 hours. On large cells, you might have to wait 30 hours at an elevated temperature. Then you do this pre-charge, which is like the first stage of formation. And what happens in that, your electrolyte does some electrochemical degradation on the anode. It creates what we call an SEI layer, which a solid electrolyte interphase. Some people call it solid electrolyte interface. I think phase is the correct term, but people use them interchangeably. There's no standard. This SEI layer happens. You can't stop it, but it also turns out to be a protective mechanism. Yeah. But when an SEI is formed, you also get gas given off. It creates gas. And the problem is if you fill your cell, seal it up, and then send it directly into formation and aging, that gas will blow up your cell like a balloon. Uh-huh. So you have a degassing phase, which is sort of this pre-charge plus putting it under vacuum to pull the majority of the gas off. Then you seal your cell. So for instance, you might put a little plug in it and laser weld it shut. But remember, you're now laser welding a cell that's got flammable material in it. Mm-hmm. And it's partially charged. So sometimes bad things happen. Yeah. Let's leave it at that. Then you go into formation and aging. Mm-hmm. Formation and aging is where you're doing your initial charge and discharge cycles, because it's not really a battery until you've charged it up and discharged it and charged it up a couple of times. And let it sit to let more electrolytes soak in, and let it sit to let the SEI layer, the solid electrolyte interphase layer form. And it's basically a series of very slow charges and very slow discharges. And then sometimes you let it sit for 24, 48, 60 hours at high temperature, depends. Well, what should I use? A lot of trade secret in there. I don't know. What's your anode? What's your cathode? What electrolyte did you use? What's your cell design like? Depends. There is no recipe. I mean, each company has its recipe, but the formation and aging can take anywhere from 2 to 7 days. And because a lot of that's just letting the cells sit. But 2 to 7 days, when you're doing, let's say you're Panasonic at the Gigafactory in Nevada, and you're doing cylindrical cells. All right, they're not that big. Let's say you're doing 1.5 million cells a day. Well, if your formation and aging took 10 days, I'm just making that up. It's not what it takes, by the way, but I can't tell you. And you're doing 1.5 million cells a day, that means you are holding 15 million cells in volume during formation and aging at any given time. That's a lot of space.
Yeah.
That's a lot of energy. That's a lot of time, and that is really expensive. So energy-wise, usage-wise in these things, the real energy killers are the ovens when you're drying your electrode and the formation and aging.
Okay.
Those are real energy killers, which is one of the many reasons that people try and site these factories by areas with really cheap electricity. Because the electricity that you use to run these operations and the dry rooms and all that, I think the third is the dry room. The third largest electricity usage is probably the dry room. Dry rooms themselves, just dehumidifying. Of course, you use less electricity to do that in the Middle East. That is for darn sure, because your natural air is drier, so it costs less to dry it, right?
Yeah.
To dehumidify it.
And the good thing is that there is sun, so you can build a solar power plant beside your gigafactory. That's
100%.
cool, huh? Yeah.
100%. It's like a self-licking ice cream cone.
Yeah.
So once you've been through formation and aging, there's a bunch of testing. You might wrap your cell. You might put a sleeve around it. Some people don't put sleeves around it. You sort of do a final testing and inspection. There's all sorts of quality control steps here as well before they go out to either your customer or to your next process line. It's you weigh them. Was there enough material? And all these cells get weighed multiple times. So you confirm that you got enough electrolyte in because you know how much your can weighed, you know how much your jelly roll weighed. You confirm that the voltage is right. You confirm that there hasn't been too much self-discharge, which would indicate you have a short inside the cell. You look at the internal resistance. There's a million things that you check. But you've been checking these things all along. I have completely missed all of the quality steps, which as an ex-quality guy is probably an egregious foul. But we could spend 3 hours just talking about quality checks. And then you package them up and you ship them. I wish it was that easy because it's not. But
yeah, it's not. But before we ship them, I would like to have, because once I heard that from you actually something about formation. It was funny to hear that formation is the phase where a lot of gigafactories get burned, or a lot of cell manufacturers facilities get a lot of fires in this phase, right?
So if you have, let's say, a defect in your cell that didn't get caught earlier, maybe a little burr sticking out, and during charge and discharge and formation aging, things swell and they relax and they swell and they relax, and you get that little short, you can get a fire. Now you could say, well, I'm going to have great manufacturing. I'm not going to have a cell defect. I'm not going to have any fires. That's what everybody tells themselves. Everybody gets battery fire. The thing is if you accept that, you don't have to like it. I mean, you obviously try to never have a fire in formation and aging. You try to never have a fire anyway. But formation and aging equipment is set up for this. There's inline, there's it self-detect when there's a voltage short and it pulls things out, and there's robots that come in with firefighting equipment and robotically spray it down. And there's good formation and aging equipment is basically predicated on the assumption that at some point, maybe once a year, maybe twice a year, you're going to get a fire.
Mm-hmm.
And the key is to just not lose your whole factory. And there have been many factories over in Asia where entire factories have burned to the ground in the early days of lithium-ion batteries. And then we learned, and we put in firefighting equipment in the formation and aging equipment, and it's fine, right?
And I hear that the formation now is like most factories really split it as in a separate building, even the formation and aging, correct?
Yeah, you will either put formation and aging in a separate building so that you do not lose your whole building. Although again, with current equipment, you shouldn't lose your formation and aging building anyway.
Mm-hmm.
Here's what happens. A cell catches fire. That's okay. There was a defect. Now you're set up for a long investigation, because you don't just go, oh, it caught fire and move on. Now there's this triggers all sorts of investigations, but you have to figure out why. How did we miss a defect, right?
Mm-hmm.
But a fire happens. The operator gets notified. They put on whatever protective equipment they need. They evacuate the people who don't need to be there. The robots go in and they do the firefighting, and then you might have to go in with an extra blanket and pull out a cell or drop it in the dunk tank or whatever it is. It doesn't need to be a reason for panic. I mean, like if a house catches fire, yeah, you should panic and you should run out. Well, you shouldn't panic, but you should run out. But the firefighters run in, right? Because they know how to deal with it, because they're firefighters. That's what they do.
But this
is fire. Here I go.
Yeah, but we have to emphasize here that we are talking about the level of Tesla, Panasonic, and LG Chem. This is the Mercedes manufacturers, huh? So in this case, the firefighters are trained. In this case, you can fight it. In this case, you can do it. But unfortunately, we see in many countries, especially in Asia, India, and this region, there are disasters which happening because of manufacturing problems and people not dealing with fires in a good way in the facilities, or thermal runaway along the street. But I guess I wanted to emphasize this formation point because I remember it was one of the things I had in mind since I heard it, that it's not an easy phase to be done even. And the second question which I have is that some people, I heard that they get dry cells from a manufacturer, maybe an Asian manufacturer, Chinese manufacturer, and they do just the last phases. So is it feasible to do this? So just to relate my question to the process, they just get, I guess, to this phase here as a cylindrical cell, and then they do the electrolyte filling and the formation and everything, sealing, cleaning, and so on.
Sure. Yep. There's companies that do that. It depends how you split up your manufacturing. There's companies that start at cell assembly and they just get coated electrode rolls from a manufacturer.
Mm-hmm.
It depends how you want to set up your operation. I do want to say one thing just so I don't get misinterpreted. I am not being flippant. I'm not being casual and cavalier about cell fires. When a cell fire happens in a formation and aging, and it will happen, it's just a fire, you deal with it, but you are trained to deal with it. The fumes given off by a burning lithium-ion battery are super dangerous. People dealing with it are wearing full face mask respirators and protective equipment. If you have, and I say that because if there's, you've got a e-bike or a e-motorcycle and the battery catches fire in your house, do not breathe those fumes. That is not a standard fire.
Yeah.
Okay. So I want to be super clear. I'm being a bit, oh, don't worry, it's a battery fire, happens all the time, formation and aging. Well, yeah, asterisk, if you have the right equipment to keep yourself and your coworkers safe while you're fighting it.
Yeah.
I'm not saying, it's a battery fire, don't worry about it. Just go pick it up and roll it up in a blanket. Because if you breathe those fumes, you can permanently damage your lungs. Permanently. There's no hospital that can do anything for you.
Yeah.
You will have breathing problems the rest of your life. Super serious.
Yeah, that's the point. Thanks a lot for emphasizing this, because I always say if you see white vapor comes from outside of the battery, you have to run fast. If it's black, you have to run, but not very fast. So this is my code, which I always use. So if it's white, you have to run very fast. If it's black, you have to run as well, but in a lower speed it's allowed. So people really have to have the right way to do it, and in factories, in gigafactories, for sure this will happen. I just want to ask about this cleaning stage here, because I guess I did not exactly understand how important is it to clean the cell. Is it does it have to be done as well accurately, or it just
There's the cleaning. Well, the cleaning / washing. So you remember, you usually get little bits of electrolyte residue on the cell, and so you need to wash those off. So they'll literally wash a cell in water, sometimes water and detergent. It depends who's buying the cell, what level you clean it to. It depends if you're self-consuming it into a module via robots and how much you need to clean it. Electrolyte residue can be corrosive. Well, first of all, it's hazardous to humans, so you want to wash it off. It really is good. How much and how you clean it really depends on who you're selling it to and how they plan to use it.
Okay. Yeah,
I mean, the general assumption in a battery factory, even on a finished cell, is you never handle it without gloves. That's just, you probably could pick them up with bare hands and be fine, but the problem is that always true? And so you have a standard. You just use gloves.
Use gloves. Okay.
I myself have picked up an 18650 and shorted it on my wedding ring.
Yeah.
Because I wasn't thinking, because I was careless and I wasn't following the rules.
Yeah, it did happen to me with a build before. So even a build can short a module, and then you will never recognize it, because you will think you will work. As you mentioned, people think, okay, I'm a good producer, I will not have fire in my formation or aging, or I will not have fire in my battery. But a good battery design or a good factory design will put a probability that I 100% will have a fire. It's the same of handling a battery that people really, I see myself, especially in the Middle East, people really handling lithium-ion batteries like they do with lead-acid batteries, without any way of self-protection, and they think it's an easy thing to deal with. And this is the main message, one of the main messages which we have to get through here, that as well, it's not easy to deal with them.
Don't take this on the Middle East. This is everybody.
Yeah, that's correct.
This is not a Middle East problem. This is an America problem. It's a Canada problem. It's a Africa problem. It's a Europe problem. And people will generally learn more and more. But it's a problem for everybody.
I totally agree. I'm just giving an example of what I'm seeing, basically, because we have a peak of EVs infiltrating the market, and people are get exposed to batteries, and they want to know what is inside it and to open and think about it. But let me first thank you for this crash course about manufacturing. I guess what you shared with us is worth a lot. Really, it's really worth a lot to have such an overview of manufacturing step by step for different types of cells. I guess the people working in the industry will know how valuable it is to share such a knowledge. And I will open the space always for questions. If there is any question or anything related to the process which we did go through, even if there are questions online, we can take them. But I don't know if you need to add any last words about those steps. I guess the main messages which I get out here, I was writing really what you are saying as a note, is that accuracy is a major role. It's very energy intense process. It's very investment, so it needs really very high capital investment to be done. And it's not enough as well to have the right equipment. You need to have the right people who are running the equipment, and you have given us many examples.
And it takes time to learn to have you could have the right people who don't know the process. And it's just, this is why I have yet to hear of a gigafactory getting set up that wasn't complete chaos for the first year.
Yeah.
It's just the nature of the beast.
Mm-hmm.
I would say the other thing is, this is any one of these steps, and I've skipped by steps, right? Any
Mm-hmm.
one of these steps is a 2 to 3 hour discussion.
Yeah.
Laser welding. I could go on for 2 to 3 hours on all the problems with laser welding.
Yeah.
I lid to a can, literally. And so, but I mean this, and maybe I can't remember what section you wanted to do next, but this gets to then, wow, if somebody's there saying, I see that there's going to be, I hear that there's this huge job need for people in lithium ion batteries. I'm an engineer or a scientist or an operator. I'm somebody who does assembly, and I want to, what do I need to learn to get into this? And the answer, and you're not going to like this answer, is, well, you should know the generalities, which are things like talks like this. But if you're an engineer and you want to be a process engineer, you're going to have to specialize in something. Mm-hmm. And it could be laser welding, in which case, laser welding aluminum is a science unto itself that has nothing to do with lithium ion batteries. It's just a process that resistance welding, ultrasonic welding, ultrasonic welding, the battery industry did not invent ultrasonic welding. They just happened to use it, right? Roll to roll processing. Battery industry didn't invent that. The paper coating industry invented that, right? Mixing and some of the other stuff is a little bit more. Formation aging is definitely very specific to batteries. But, as a great mechanical engineer, you don't need to know cells. You need to be a great mechanical engineer. Or as a great chemical engineer, or a process engineer, or a quality engineer. And I'm using engineer just because that's what I'm most used to hiring. But I've also hired technicians and operators, and I guess let me just run with that and say something about what I've looked for when I hire somebody and some of my frustrations. Mm-hmm. And I'm going to talk about some of the higher education positions. But I'll also then go down to sort of the entry level stuff. So when I'm hiring somebody to be a chemist in a lithium ion battery company, what I actually want the most is for them to be a great chemist. And that has nothing to do with batteries. So for instance, here's a little tip if you ever interview with me and you're a chemist. My first question is, go to the whiteboard and draw the periodic table of elements from memory. And usually you get some surprised looks. I certainly don't expect anyone to draw the entire periodic table of elements from memory. But if they're actually a chemist, they should be able to get the first few rows. But I'm a nice guy, and usually they'll say something like, well, we weren't required to learn that. And my thinking that I don't say out loud is, I don't care what you were required to learn. Do you love chemistry? Because if you loved chemistry, if you're a chemist because you love chemistry, you would have memorized a couple of rows just for fun. But okay, I can understand, maybe I'm not going to throw out an interview because of that. So then I say, okay, that's fine. Then go draw the shape of the first 3 or 4 rows of the periodic table of elements using electron orbital theory. And that they should know. Now, there may not be any chemists on this particular call, but electron orbital theory says that there's electron orbital shells and electrons are paired, and there's the 1s, the 2s, the 2p, the 3s, the 3p, right? And those have 2 electrons, and the s has 1 pair, and p has 3 pairs, and sort of 6 electrons. And by doing that, you can actually draw the periodic table of elements. That big little thing that looks like a little hexagon thing.
Yeah.
Like that isn't just somebody randomly ordering them in the order they were discovered. Like there's actually meaning to that table, and that meaning has a chemical basis that is the core of chemistry. And so when I interview a chemist, I don't give a damn if they know lithium ion battery chemistry.
Mhm.
I can teach them lithium ion battery chemistry. If they're a great chemist, they can learn lithium ion battery chemistry. If they're a great chemist, they can learn anything. But if they've just studied up on lithium, how an anode and a cathode works, I'm happy for them. I mean, it makes my job easier. But what I really want is a good chemist. If I'm hiring a chemist, I want a chemist. Same thing with mechanical engineer.
Mhm.
If I'm hiring somebody to be a their main job is to be a mechanical engineer. I actually don't care if they know all the steps of lithium ion battery manufacturing. I don't even care if they know an anode from a cathode. What I do care is that they know mechanical engineering and they know what Moore's circle is and von Mises criterion and can draw a stress strain curve and can tell me what the force equation of a spring is. And, I'm not a mechanical engineer, so I'm at the end of the questions that I ask, but a great, and we're talking just engineer for now, a great engineer, mechanical engineer, if they've been working on combustion engine blocks, will be a great engineer working on production equipment for lithium ion batteries. They'll be a great engineer for design, for CAD modeling, computer modeling a shell of a lithium ion battery. Yes, they will need to learn lithium ion batteries. That is true. That would be very helpful. And they will have to learn it. And the less they have to learn on the job, the faster they come to speed. But if they're not a good mechanical engineer, it doesn't matter how much they know about batteries. They're just not a good mechanical engineer. And if I'm hiring a mechanical engineer, if I'm hiring somebody to do mechanical engineering work, I want them to know that. So this may not be what people want to hear. I mean, yes, if you're interested in batteries, you should certainly learn about all the steps of batteries. Why should you do it? You should do it because you're interested in it, right?
That's right.
You should do it because it's what you want to know and you're curious, and that's awesome. When I am hiring somebody to be in a particular position, I want them to be good at that core skill set. So a bad quality engineer who's worked at a battery factory before is not helpful to me in comparison to a great quality engineer who doesn't even know how to spell battery. They've been maybe working in the pharmaceutical industry, on drug delivery quality. The principles of a quality engineer are the same. Now, they're going to have to learn about batteries. They're going to have to learn about what's important and what quality metrics are important and what's important to quality. And but the fundamentals of how a quality engineer does quality, same on any industry, right? And I want a great quality person to do quality more than I want a mediocre or bad battery quality person, because then they're just going to be mediocre or bad at my company too.
Yeah.
And then I got to teach them how to do their job. It's easier for me to teach somebody about battery manufacturing than it is for me to teach a mechanical engineer how to be a mechanical engineer, because I'm not a mechanical engineer. I can't train them what they should have learned in school. I can't train a quality engineer how to do quality principles, because that's not my background. I could teach somebody to be a decent polymer chemist because that's my background. But every other discipline, I want them to arrive from school knowing the fundamentals of their discipline.
Yeah, I got the message. So the most important is that they understand the fundamentals which they are working in. But did you see this also in Tesla and Northvolt, or there is a different work culture between Tesla in the US and Northvolt in Europe in terms of hiring people and the quality of people they are looking for? Because now we are talking about the world-class places where people can work in.
Well, I think it depends more on what you're hiring for. So when I started at Tesla, I was in the corporate office where all the sort of the thinking goes on and design, and like the battery and the module design people, not the battery cell, because Tesla didn't make cells when I was there, but the modules for like, and the battery for the Model S, let's say, the 7,800 cells assembled in a really cool way. When you're interviewing for there, Tesla's a little unique. And I think the world is finally seeing that as they watch Elon take over Twitter, which is not going well. But and let's leave Elon out of this. But the core culture at Tesla is you will be excellent or you will not get a job. And if you somehow get a job by not being excellent, you will not have a job within 6 months. So,
can you please repeat this again, because I did not catch it? So the work culture is
you will be the absolute best of the best.
Okay.
Now, this is for the high-end design teams designing the next car, designing the next heat pump, designing the next seatbelt system, designing the next autopilot. Like this is, they really are the best. I will give you an example that actually includes Elon. One person, a friend of mine, was trying to hire a mechanical engineer in the corporate office. The kid went to a great school, but not Stanford or Caltech or MIT, but he was super smart. He went through 2 levels. He interviewed with 7 people. Every single person gave him the heads up. He was a great mechanical engineer, awesome grades, done a bunch of his own projects. He'd worked on a solar race car project, with a team in college. So this resume, because Elon takes the design team very seriously, the resume goes in front of Elon, and Elon goes, "Oh, he was on the solar race car team. Did their team win?" And he goes, "No, they came in second." He goes, "Not hiring them. We don't hire losers."
Oh my God.
Now, that is, of course, patently ridiculous. I am not completely disagree with that point of view. Completely disagree.
Yeah.
But that's sort of the culture. Now, let's talk about that's the cream of the crop for design. But let's be real here, okay? Let's say you're now at the Gigafactory in Nevada. Yeah, if I want a production engineer, I need a really good production engineer. If I need a quality engineer, I need a really good quality engineer. But what I really need in production are good people. You don't have to be the smartest person. You do have to be a person who cares, right? There is a distinct difference. You can achieve a lot in your life by passion. Not everybody is going to be the smartest person in the room. And quite frankly, if you're working in a production setting, do you really want to hire crazy far out thinkers? No, you want people who are good people, who are honest, who know how to do a hard day's work, who can do something consistently, who will speak up when they see a problem, but who are also good humans at communicating, so that if I'm angry at you for something, I don't come and scream at you. I come and have a discussion with you and say, "Hi, I'm Ahmed. I'm a little angry with you because of this." And then you say, "Oh, I'm really sorry, but this is what I intended." "Oh, my mistake." You can have the relationships count.
Yeah.
So when you're hiring, so there's the corporate high-end engineers, but then there's the reality of having a 60,000 person company or whatever they're at. And the tendency is for someone to say, "Oh, we don't need as high a quality of a person for a manufacturing environment." And I think that is a huge mistake. You need just as high quality of a person. You don't necessarily need cutting edge skill set. Does that make sense?
Yeah, I would expect this in the European culture, but I did hear before about the Tesla culture specifically, and I totally agree with you that even there is a lot of teams in football. I'm not a football fan, but I have seen this repeatedly happen, that when they try to gather a lot of stars at the same table in the same team, they never win. Because it's not about having the best of the best. It's maybe now it's a matter that there is a proven record of Tesla specifically in the market. So, but this proven record, because we have big players getting into this field now and focusing directly on it. Speaking on the German manufacturers, Mercedes is getting full electrical, BMW is doing this, Volkswagen is doing this, and those are companies who have hundreds of years of manufacturing culture and team working. So it's just a ramping up issue, and then you will see the difference of the culture. And to be honest, I'm a fan more of what you have said, that a person who's knowing how to deal with others, a person who understands the fundamentals, of course, perfectly, he will be a person who knows as well something about the industry he works in, is much worth than having the best graduate out of, you graduated from MIT yourself. So you know how it works in big
Yeah,
universities.
and I thought I was smart, and in hindsight, I knew nothing.
That's correct, but
if I could go back in time and talk to my cocky, arrogant, all-knowing self, I would smack myself upside the head and say, "Shut up, listen, and watch how things actually happen, and learn how to be a better person." That's what I would tell myself.
Yeah, I guess this is what happens by every human being who gets really wise by time, huh? It's the building and process, but I mean, you gave us the key of qualities which you are searching for, which can be applicable to all the people who are listening to us, who wants to build a career out of it. So the main issues which we can agree on is that, because a lot of people tell me personally that they want to do maybe a PhD, but he did not graduate with high marks. I personally did not graduate with excellent I graduated from Egypt, my bachelor, but it doesn't really make a big difference that you had A plus or excellent, or this is not the main issue. The main issue is that what you can do, and as you mentioned, are you able to emphasize the idea of specialization? Because this is the second main point I get out of your points you mentioned, that you need to specialize in this current world which we are living in. To build a career, you cannot look around everything. You need to be very specific and really get deep, very deep inside. But this is maybe applicable in industrial countries or places like, for example, Germany, Japan, US, and. But unfortunately, in other places where there is no R&D, what is your advice for people who really working? And I have worked in Egypt myself, for example, and there it's rarely to have R&D. It's like, I would not say impossible, because there is an R&D, but it's very rare. So it's mainly sales, service, and so on.
Well, but humans are still here. I mean, define R&D. Okay, maybe there's not drug delivery R&D and battery R&D. I'm taking this away from the battery space. But necessity, as the saying goes, and I'm sure there's an Arabic corollary that was invented before this one. Necessity is the mother of invention. Is the English phrase. I'm sure there's an Arabic corollary to that. And you can't tell me. I mean, I've been through all over this world. I've been in 50 different countries, and I've been in the Middle East. I just went to Jordan this last. Oh, love Jordan 5 times. Amazing. Love it. But you get to some of these areas, and the way that people have taken what they have and built a system that works, that's invention, right? Now it's not the same. You're limited by your resources, certainly, and so the type of invention you're doing might be more mechanical or building science, or agriculture invention. But there's still, humans are still inventive. Well, I agree with you that from an engineering standpoint, there's certainly not as much. I thought there was a fair amount in Morocco, though. Yes, I mean that's sort of more North Africa than Middle East per se. But if someone were saying, "I want to get into the lithium-ion battery industry," I would then, my initial thinking would be, well, first, become good at something, right? If you're an academic, I think you have 2 routes. One would be to become really skilled in a particular area of expertise, and then unfortunately look at one of these other plants that's being set up somewhere else. That does not bring that knowledge to the Middle East, though. That is a problem, right? The other approach is to not start at the cell level, but start more at the module and pack and electrification level. So that's where you're talking about circuit design for a safe battery pack, assembly of cells with cooling, and it's a decent example. Like out of Taiwan, that company Gogoro, who does these little battery pack e-bikes and e-motorcycles, right? Now they're not building cells, they're buying cells. They're not making their own cells. They did design their own packs, but they also designed their own chargers and their own charging electronics, and they've got quite the little business model. And there's been a bunch of copycats on that, including in India is starting to ramp up on this. And India has had, if people have seen it in the news, a whole bunch of problems because they've been bringing in electric bikes and electric motorcycles that are not made well, probably bad charging circuitry. It's probably less the cells and more the charging circuitry. And they've had some fires and people have died. It's been really bad. The other problem is the ambient, the standard temperature in India is not the standard temperature in Asia. And it's not the standard temperature in North America. And a lot of people cells do have an upper temperature limit. And so your temperature control and temperature monitoring needs to be better in hotter environments. And so India actually has a lot of corollaries with the Middle East.
That's right.
But at the end of the day, it's pretty clear that the Middle East, from an economic standpoint, could easily, like China and like India, really take a leap forward with small electric vehicles. I mean, maybe there's some people here who will start the next Tesla, and that's awesome to start the next Tesla in the Middle East. But you could also start with, you know what? I'm going to import electric scooters and build the architecture around that, the business architecture. And then we'll build our own battery packs for those scooters that meet the open standard for those scooters. And then we'll start building our own scooters, that take those battery packs, and we'll build this ecosystem. And I'm making this up as I go. And you and I, before this call had started, I mean, there is a lot of good that can be done in that area, and we talked about, and let's not get political, but I'll bring it up anyway. Violating my own rules. I mean, Palestine could do well to not have to import oil for people to get around and do their work, and also be able to use that scooter pack charged off of solar panels to drive lights at night when power gets cut, right? I mean, there is a freedom there that is powerful. I did hear an interesting quote in a podcast I was listening to the other day, though, when somebody was, it was a woman who was doing electrification projects in Africa, and she said that one of the village chiefs said to her, "Today we spend our money on batteries to give us light. Before, we spent our money on kerosene to give us light. But either way, they're still taking our money." And it was an interesting perspective, because I think this is where you're going with this. How do you keep the money local? Right? I mean, we can all agree that EVs are better than gas cars. Sure, why not? Right? But there's that urge to get local industry. It's not just who's making money off of it, but how do we create a culture and an economy that's self-sustaining? Keep the money local. I mean, at least when you buy batteries and some solar panels, even if you didn't make the batteries and the solar panels, now you can at least not get charged for gasoline and kerosene all the time. But she was right. You're still giving somebody else your money.
That's correctly. That's totally. And I would like to get back to the point of India, because you have raised a very interesting point, which we did just have it in the last seminar. So actually, the 2 points, the one related to Palestine and related to India. But let's comment on the Palestine first. You have given a very good example of people living with a very limited type of resources, and still they are able to produce energy, and they're surrounded from everywhere. So there's no excuse. And actually, they are heroes to do this, from my point of perspective. And the second, India is really, people are saying, we had a discussion last week about some projects going, namely in Egypt, and the students were saying, why we don't do this? The people are doing this in India. And my comment was that you have said this because you don't know what is happening there. They have just seen that there is a rise of use of EVs and so on. But by this time, I did not share. I just Googled the news. Look, EV fire rises in India, and there is a restricted policy. Um, uh, India EVs play a hell of a government. There's a lot of things that happen in India which we have to learn from. And as you mentioned, really, India is very near to the Middle East as a culture and as an environment as well. But people are just selling out they are, maybe they are not aware, and this is part of this work to make them aware, or maybe they are kind of taking for granted that the problem will solve itself. But what is happening on ground is that there is, whenever you play around with something like a lithium-ion battery, which has a lot of energy inside it, then you will really, if you don't treat it in a correct way, you will run into the same problems. And this is what we see in countries, a lot of countries in the Middle East happening, that a lot of do-it-yourself batteries, self-made things, things which we call under the table made and so on, without any controlled quality, things getting cells. And you mentioned the point related to getting cells into modules. That's why I shared this graph here. So I guess you mentioned, okay, after getting a cell, we have to, still there are many steps you have to master. And as you mentioned, each step we can spend maybe days just talking about it. And people think that it's easy because I have the cell, so I can go from cell to module. So today we have learned that cell manufacturing challenges, but still there are a lot of manufacturing from a cell to module. I guess we can do it then in the next seminar or something, because it will take a lot of time. But this is the main messages here which we want to deliver, and I'm very happy that you have highlighted this. So I totally agree to your point of view, and still there is a potential. We are not saying that things are closed or it's impossible, but from my perspective, people have to know what they are getting themselves through, especially investors and technical people. It's not doing this and having a battery manufacturing industry.
Right. Well, I mean, and there are other places. Remember, we just talked about cell manufacturing. Then you're talking about module and pack, which could be just module if it's an e-bike or an e-scooter or or a bicycle conversion with electric to get people and to go 50 kilometers to get to town. Or maybe it's and that same battery pack can take in solar power, and the power electronics are designed to be safe by varying voltage inputs. But there's also the other end of it, which is the raw materials. I mean, it doesn't take too much Googling to figure out that there are not enough lithium mines, not enough cobalt mines, not enough, now these things take lots of time, lots of money. I mean, we're talking 5 years, $1 billion kind of thing. But, the geography of the Middle East really lends itself towards a lot of that. Like, for instance, I know people had said that Afghanistan was the Saudi Arabia of lithium, right? Now, I don't know if that's true or not. And obviously, doing business in Afghanistan might be a little difficult right now. Well, certainly for somebody like me, but there is cobalt in Afghanistan. There's tons of lithium because that type of environment. Where's lithium? Bolivia, dry environment. Western United States, dry environment. Australia, dry environment. I will bet you there is lithium all over the Middle East. I'll
Yeah.
bet you the Middle East is the lithium. I'll bet Saudi Arabia is the lithium of Saudi Arabia, right? I mean, you know, it's almost comical. It's probably also there.
Yeah.
And so, from a mining and metallurgy standpoint, Middle East is probably sitting on a pot of gold. It's just nobody's thought of it that way. You know, instead of drilling the oil, you know, I mean, and you need to mine responsibly. And, you know, mines aren't exactly wonderful places, but it has to come from somewhere.
Yeah.
And, you know, I would be shocked if Morocco didn't have mineral resources like crazy. I would be completely blown away. I spent time in Morocco, and just the very geography, there's no way that there's not huge mining resources there.
Yeah, it's just about exploding. I guess the opportunities are there, and but there are some barriers as well. So I believe, from what I have seen, is that people still take things for granted. But as you mentioned, it could be that we are sitting on treasures and we never know it. I remember Turkey just announced that they have found a big stock of lithium-ion battery materials, but I guess this is as well a topic by itself. So, but still we can explore the opportunities, and we can hopefully. I would like to take a commitment from you to have a follow-up seminar where we
Sure.
can, because I guess we are now about 3 hours. I don't want to to push a lot on this. So this time probably we will not be able to have a lot of discussion about the post-sell things, like having a module, a pack, and a system level. And as well, we will leave the audience to digest the information which we did share about cell manufacturing and come up with any questions. And the career part as well was very interesting. So if you have any final comments, please give it to us, or otherwise. But before the final comments, we just need commitment of the next seminar. This is very important.
Sure.
Sure. Okay.
I'm happy.
There is one question as well in the background, just for the info.
Okay. Do you know what the question is? Because they have to ask.
I don't know it, and actually he just raised his hand, but I cannot. Ali, I cannot unmute you. I guess you have a problem in your settings. So please, you can write the question in the chat. Okay. Here it is.
First of all, I would like to give you a special thanks for this interesting meeting. Really, I feel phenomenal after this worthly information. The question that, as you know, I'm studying renewable energy engineering. I'm originally from Palestine, and I'm asking you if you can help me how to get a special training in Germany. This is my dream, but needed fully funded opportunities at next summer.
Is specifically in Germany, or in general, you mean the opportunities of a fully funded programs?
Especially in Germany.
Okay. I guess you can give.
So I think it depends. So there are certainly, like, I can speak for, I don't work there anymore, but for, you know, Northvolt in Sweden, you know, their policy was generally like this, because they're a startup, right? And they're big, but they're a startup. They were certainly looking for great engineers. For students who wanted to do a summer internship, what they would not do is pay for travel, but there was a stipend once you got there, and they would find housing for you and get you paid, you know, a little bit as a student. If you are finishing up your degree and are looking for a career, then that drops you into the more standard application process. And if you have, like, for instance, for various, you know, energy applications, even if you were doing, you know, wind and solar, but you wanted to go into batteries, again, if your engineering fundamentals are strong, then that's fine. It shouldn't restrict you to wind and solar. in which case, you've got to go peruse the website of open positions, of which there are a lot at various companies, and start applying. Also, use LinkedIn. Find out if there's anyone else that you know, or that you know who's there, to help get your resume floated to the top. A lot of times you don't hear from companies just because they get 1,000 resumes for something. But I know Northvolt, for instance, has, I think they have 63 different nationalities working there in Sweden. Sweden's a little cold, colder than Germany, sorry. They have, I think, 60 some nationalities, people from all over the Middle East, from India, from Asia, from the US. And they don't care where you're from. They want good engineers. They want good people. They want good manufacturing associates. You don't even have to be an engineer. You could be a machine operator, and then learn the trade and work your way up. If you were willing to, God save you, move to Skellefteå, Sweden, which is northern Sweden, which is really cold.
Yeah.
They are actively looking for good, smart, eager operators. It's not a glorious position, but then in a year or two, you've learned about, let's say you're in formation and aging. Now you know a lot about formation and aging. Now you can become a shift lead of formation and aging. And it's a long road to work your way up. I'm not going to lie to you. But I don't have any handouts, but the potential is out there.
Really, I am very inspired to learn more about wind energy modeling for multi-rotor systems.
Okay, I can give you advice on this because I studied renewable energy masters. Actually, north of Germany and Denmark is the right place for this. But I would recommend that you can easily, as Ken mentioned, he gave a general career advice. Look up LinkedIn, look up the right people, and look up the companies who are working in your field, whether it's batteries, renewable energy, anything. And there is one thing which I add to Ken advice, and this is maybe will be the last comment which we have because of the time, that do not be shy that you are coming from the Middle East or Palestine or whatever to apply. Just have the courage to apply and say, okay, what do I have different from the people there? This is really what is missing from people coming from this area, because I'm coming from this area. Just apply, and you have only two options, whether to fail or to succeed. But if you do not apply, you have only one option, that you are failing already. So it's the same result. So this is really what makes people afraid. They think, okay, I want to play it safe. If I apply, they will never get me. Their name is too big, or this is not how life works. Really, this is not how really things work in reality, based on my small experience. And Ken can emphasize this totally. And this will be our closing point, and we can discuss more in the next seminar for sure.
Yes, I applied before to the Sandiana National Renewable Energy Laboratory, but because of COVID-19, this meetings was cancelled and began line.
Yeah, just apply again. It's there are a lot of things can happen. It's not the issue. So this is the main message here.
Yeah, COVID was a complete disaster for everybody.
Yeah. Okay, so I would like to stop here, Kim, because
the earthquake.
Yeah, it did affect everyone. But I would like to, at the end, really thank Kim very much for this complete 3 hours of sharing the battery fundamentals, or 2.5 hours maybe. This is really, really a very appreciated time. I guess people who will work in the future in the battery industry, they will get back to this recording and really look for it again and again to understand the basics of cell manufacturing. And I really learned a lot and take a lot of notes, because cell manufacturing is not a part of my deep specialization. So I did really learn a lot today. And I would really thank you for all the tips which you gave us about the career things. And as we mentioned, we continue in the next seminar, hopefully soon.
Great. Thanks for having me. It's an honor.
So I would hand to Ala from Egypt scholars to close the session if he's still alive, because we always take a lot of time and those people are not still alive. But Ala, are you still here? I guess not. Yes. No. He's still with us. Yeah, he's sending me in the chat. Okay. Yeah. Okay, so on behalf of Egypt Scholars as well, I have to thank you as well for the time, and hopefully we arrange the next seminar soon. So thanks everyone, and have a great time for you.
Awesome.
Have a
Thank
great
you.
day for you and night for all of us.
All right.
Okay, thanks a lot.
You bet. Shukran. Bye.
Bye-bye.